So yesterday we were discussing about the lattice vibrations of one-dimensional monoatomic chain in which we have n number of unit cells in the crystal, and this means that to every unit cell only one atom is there. So for such one-dimensional monoatomic chain of atoms, we calculated the dispersion relation between the frequency and the wave vector, and we proved that omega is equal to omega max times sine Ka by 2. Here omega max is the maximum frequency that the lattice can allow to pass, and it is mathematically given as 2 under root k bar upon m, where k bar is the spring constant, and so its value is around 5 into 10 to the power 3 dynes per centimeter for the crystals. And if we consider the hydrogen atoms to be arranged in a one-dimensional chain, then mass of hydrogen atom is 2 into 10 to the power minus 24 gram, and the frequency comes out to be 2 into 10 to the power 3 hertz, which lies in the infrared region. So the lattice or crystal can only allow the frequency in the range between 0 to omega max. So such type of crystal behaves as a low pass mechanical filter. You might have studied filters in electronics. There are low pass filter, high pass filter, and mid pass filter like this. So here the crystal behaves as a low pass mechanical filter. So this is the dispersion relation of a one-dimensional monoatomic chain in which we have the angular frequency or energy. If we multiply it with reduced Planck constant, that is h cross, so we will get energy h cross omega versus k. So we can see that at the smaller wave vector values very close to 0 or higher wavelength limit, the dashed curve and the solid curve, they match with each other. This means that at longer wavelengths or smaller wave vector, the discreteness of the solids is the discreteness of the atoms in the solid is not important. This is what we see yesterday. And from this graph, from this very graph, we see it is periodic in nature. So this means that whatever information this graph is providing in higher zone, the same information is present or same information can be translated to first Brillouin zone with the help of a suitable reciprocal lattice vector. So if we have any reciprocal, if we have any wave vector k prime that lies in the, for example, second Brillouin zone, it can be translated to the first Brillouin zone with the help of a wave vector given by 2 pi upon a. Therefore, the two k values, k lying in the first Brillouin zone and k prime lying in the second Brillouin zone, they are symmetrically the same. They are symmetrically same. So then we calculated in the long wavelength limit, we get the same type of relation. Omega is equal to Vs into k, where Vs is the velocity of elastic waves propagating inside the solid. And using all these things, we calculated what should be the spring constant for this monoatomic chain. When k increases, means we are moving towards the zone boundary. So we see a deviation in the behavior of omega k, and at the zone boundary you can see here that its slope becomes flat. That's why here we will have the zero group velocity. As we will see, we will prove it mathematically that at the zone boundary we will have the zero group velocity, means an elastic wave whose wave vector is of this much length, 0 starting from 0, and it terminates at pi by a. So that elastic wave will be reflected from the atoms, and the interference of these two traveling waves, but which are traveling in the opposite directions, their interference will give rise to a standing wave. And as the name implies, standing wave does not transport energy. Therefore, the velocity of this what you call this standing wave will be equal to 0, and hence slope here, because omega, the slope is given by on this graph it will be given by del omega by del k, so slope here would be equal to 0. This means the velocity, the group velocity of the wave would be equal to 0. Now we talk two types of velocities. One is the phase velocity, and the other one is the group velocity. So I hope you understand the difference between phase velocity and the group velocity. If we have only single wave, single traveling wave, so the speed with which any point on this wave, which is a constant phase, so that point travels with what speed is given or is defined as the phase velocity. In other words, the speed or velocity with which maximum or minimum of a traveling wave travels in space is given by phase velocity. But there is another thing, group velocity. Group velocity, as the name implies, it is a group of some waves. So when we combine several waves, what we form? We form what you call wave packet. So the speed with which the wave packet travels is defined as the group velocity. So here at the center of first Brillouin zone, we will have the group velocity equal to the phase velocity. This means here only we will have kind of elastic waves that is made of only one wave, but at the near the zone boundary, because we have the Bragg reflection of the waves and we have a standing wave which is a combination of traveling waves, therefore we will have wave packets, and we will see that because it is a standing wave, so therefore group velocity here would be equal to 0. So here we define again phase velocity. The rate of advance of a point of constant phase in the direction of wave propagation is known as phase velocity. It is given as omega by k. And group velocity, the velocity at which the traveling wave carries energy, is called group velocity, or the velocity of group of waves, or its envelope. So Vg is equal to del omega by del k. Now we would like to see what would be these two types of velocities in the long wavelength limit and in the short wavelength limit. So in the long wavelength limit means at shorter wave vector close to the center of zone, first Brillouin zone. So there we have seen that omega is equal to Vs times k. So the phase velocity can be defined as Vp is equal to omega by k, that would be equal to Vs. So Vg would be equal to del omega by del k. Again, it is equal to Vs. So the group velocity and the phase velocity near the center of the first Brillouin zone are same, and they are independent of frequency. As the curve predicts that omega versus k is a linear graph, it is independent of frequency. So this is how we can represent an elastic wave under the under this long wavelength limit. So in the long wavelength limit, the discreteness of atoms is not important. Solid behaves as a continuum. Here we can see an elastic wave in the long wavelength limit. Here lambda, the wavelength of the elastic wave, is much greater than the interatomic spacing. Therefore, under such condition, that is lambda is much greater than the interatomic spacing, the discreteness of atom is not important. Here all the atoms behave as they are not discrete. Now we consider the opposite case, where we have the smaller wavelength or higher frequency or higher wave vector. That means we are close to the zone boundary. Under that condition, the phase velocity Vp is equal to omega by k, and we know the relation between omega and k, so it can be defined as omega max divided by k sine ka by 2, or it can be written as 2vs divided by ka sine ka by 2, and Vg is equal to d omega by dk vs cos k by 2. So here we see that as we move towards the zone boundary, there is a mismatch between the phase velocity and the group velocity, and both are frequency dependent. Now we would like to see what happens when we have the maximum angular frequency, or we have an elastic wave that is propagating inside the solid, and this wave is having the maximum frequency. So that happens at exactly at the zone boundary. So the wave vector would be k is equal to pi upon a, that is equal to 2 pi upon lambda. So this means that the wavelength of such wave which is traveling inside the solid with maximum frequency, the wavelength of such a wave is equal to 2 times of the interatomic distance. So we calculate what would be the phase velocity. It would be omega max divided by k, and it comes out to be 2 vs upon pi, whereas the group velocity would be equal to 0. And this is what you can also predict from the graph, that here slope of this curve is 0. This means that the group velocity is 0 at the zone boundary. So group velocity is equal to 0 means, as we have discussed several times, this means no transfer of energy or signal at this particular frequency, and the wave behaves like a standing wave. This is analogous to Bragg reflection, which we have studied in the case of X-ray diffraction. This we have studied while we discussed the band theory of solids. So Bragg reflection is 2d sine theta is equal to n lambda, where n is the order of diffraction. For first order diffraction, n is equal to 1. And if we have normal incidence, so sine theta would be equal to 1, because theta would be pi by 2. So lambda is equal to 2d, or in that case, d is equal to interatomic distance. So lambda is equal to 2a. So we can represent such elastic wave which is of maximum frequency and whose wavelength is equal to twice of interatomic distance. So this wave, this elastic wave, is represented by this, but this is just a pictorial means for the sake of simplicity the displacements are shown transverse, but actually these vibrations are longitudinal. So here we can show that if we have a wave whose wavelength is equal to twice the length of interatomic distance, then such wave would get reflected. So if this wave is normally incident, it may be reflected from atom A, it may be reflected from atom B, but it will be reflected in the opposite direction. That's why the resultant of these oppositely traveling waves will generate a standing wave. And the waves scattered from waves or wavelets scattered from the neighboring atoms are out of phase by an amount of pi. So for example, you can see here the wave which is reflected from atom A, it is traveling in this direction also, but here you see the wave has, if it reaches, if the incident wave does not, if the incident wave does not get reflected from atom A, it reaches atom B, but it has traveled a phase, extra phase of pi. So this is what we mean to say here, that wavelets scattered from the neighboring atoms are out of phase by an amount of pi. But when the wavelet reflected from atom, for example, atom B, it reaches that reflected from atom A, the two wavelets are in phase, and therefore they will construct they will interfere constructively, and we will have the maximum reflection. We have more properties of this omega versus k diagram. It is symmetric, as we can see from the graph itself. So any k in second Brillouin zone is related to any k in the first Brillouin zone. So k prime is equal to k plus 2 pi by a, or omega at k prime is equal to omega k. This you can see from the graph itself. If we have any point here and we have any point in the second Brillouin zone on the left side, these 2 points are identical. They belong to the same k point, which are related to each other just by the difference of a reciprocal lattice vector. Now, what it will represent? So, for example, if we have any arbitrary wave vector that is given as pi upon 2a, so pi upon 2a means it will lie in the first Brillouin zone, because first Brillouin zone extends from minus pi by a to plus pi by a. So, if we have any wave vector k is equal to pi by 2a, so this will lie in the first Brillouin zone. And by the relation between the wave vector and the wavelength, that is lambda is equal to 2 pi upon k, the wavelength corresponding to this wave vector would be lambda is equal to 4a. That is one particular wave. And we can construct another k prime which is related to this k by a reciprocal lattice vector. So this k prime would be pi upon 2a plus 2 pi upon a is equal, that would be equal to 5 pi upon 2 pi a, and the corresponding wavelength would be equal to lambda prime would be equal to 4a upon 5. So now we show the two elastic waves represented by these two different wavelengths, and we would see that these, even though by looking at these waves they look different, but they represent the same K point. So this is a wave that has been shown here, and this wave has lambda is equal to 4a. You can see that 1a, 2a, 3a, and 4a. So lambda here is equal to 4a. This is a wave, and here we saw another wave whose wavelength is equal to 4a upon 5. This means in the distance of 4a we can have 5 lambda. So this is a wave that represents lambda is equal to 4a upon 5. The two waves which are of different wavelength, they exactly represent the same physical motion. This means that the two waves are physically identical. The two and physically identical means we call this as mode. So the two modes must have the same frequency, and this is true for any arbitrary k prime or k we choose, which are related to each other by a reciprocal lattice vector 2 pi over a, or in general any arbitrary wave vectors denoted by k prime and k which are related to each other by 2 pi m over a, where m is an integer. Hence, in a discrete lattice, the wavelength associated with a certain wave is not unique. I once again repeat it. In a discrete lattice, like we are considering one-dimensional chain of atoms, so in such a lattice or crystal, the wavelength associated with a certain wave is not unique, because to this wave many equivalent k wave vectors may be assigned, which are related to each other by a translation in the k space. In other words, for each particular k value, there may be several wavelengths associated representing the same wave motion. This phenomena, that two waves with different wavelengths will look same if they are sampled only at lattice points, is often known as aliasing of waves. And the one more property of this dispersion relation is that dispersion curve also shows the reflection symmetry. If we put a mirror plane, so left hand side is the mirror plane of right side, or right side is the mirror reflection of left side. So now we have discussed the dispersion relation of one-dimensional monoatomic chain. We would like to see how many k values can be there in the first Brillouin zone, and the hint I gave to you already in the band theory of solids discussion, that in one particular zone the allowed values of k is equal to n, where n is the number of unit cells in the crystal. Okay, so by looking at the continuous graph, we see that there should be infinite number of k values. If we look at this graph, so between the first Brillouin zone boundary, naively we assume that there should be infinite values of k, because this is a continuous curve, but we will prove that the k values lying, number of k values lying in the first Brillouin zone is equal to n, that is equal to the number of unit cells in the crystal. Therefore, the k values, number of k's lying in the first Brillouin zone, it is not infinite, but it is finite equal to the number of unit cells. So in order to prove this, any k values which lie in the first Brillouin zone, it represents a mode, and mode means allowed values, and sometimes we also call mode as normal modes. So basically our aim is to calculate how many normal modes or how many ways of representing the wave vector are there in the first Brillouin zone. So in a normal mode, atoms vibrate with the same frequency. Each k value in the first Brillouin zone corresponds to one particular mode, and this is why I have already said that naively means if we look at the omega versus k diagram, because it is continuous, we are compelled to think that there should be infinite values of k between the first Brillouin zone boundary, but this is not precisely correct. So in order to prove this, we consider one system which has exactly n atoms in a row, and this system of ours follows periodic boundary conditions which are given by von Karman periodic boundary condition. So if we have such chain of atoms, a chain of n atoms, so we can fold it around a circle. So nth atom and the first atom will be exactly at the same place. So this means that if I travel a distance of n plus n, xn plus n, that should be equal to xn. Or vibration of the first atom xn should be equal to the vibration of xn plus nx plus capital N vibration, and the total length of this ring is Na, because A is the interatomic distance between two neighboring atoms. So we can represent the elastic wave by e to the power iota omega t minus k an. This is for this xn. Yesterday we have seen it, and this xn plus n would be represented by e to the power iota omega t minus iota k capital N plus n times a. And after solving it, we will get e to the power I k n a equal to 1, and Na is the total length of this ring. So it should be equal to e to the power iota kl equal to 1. Though this we have already seen this while we discussed the Sommerfeld free electron theory. So this condition would be satisfied if kl is equal to 2 pi times some integer, or k is equal to 2 pi m upon L. So we see that k cannot have any arbitrary value. So there is a restriction on the k value. It can be any integer times 2 pi upon L. So this means that the k values are quantized. This means that the k-axis in the dispersion curve is a discrete set of many individual points. The spacing between two neighboring k points is equal to, from this ring we can calculate is, if we take a complete round, it will be of 2 pi round, and the total length is L. So the distance between two neighboring points would be equal to 2 pi upon L, or 2 pi upon Na. Thus, the total number of allowed modes or total number of allowed vibrations in the first Brillouin zone would be equal to what is the range of K in the first Brillouin zone divided by what is the spacing between two neighboring K points. And we know that the Brillouin zone, the first Brillouin zone, extends from minus pi by a to plus pi by a. The total distance is 2 pi over a, and the distance between the spacing between two neighboring points, neighboring K points, is 2 pi upon L, or 2 pi upon n times a, and it would come out to be n. So these are the number of atoms or number of unit cells in the crystal. Therefore, allowed values of wave vectors in the first Brillouin zone is equal to the number of atoms, and because we are considering one-dimensional monoatomic chain in which we say that only one atoms belong to one unit cell. So therefore, the total number of allowed K values are equal to either the number of atoms in the crystal or the number of unit cells in the crystal. Same thing applies to the case of band theory of solids. So since we don't have the infinite number of K values in the first Brillouin zone, therefore we can show it for just to make you clear. In this example, what we are considering 10 atoms on a string. 10 atoms on a string. So the 10 atoms are shown here. This point and this point are equivalent because they are related with the wave vector of 2 pi by a. That's why we have here 11 points. But exactly this point and this point are the same. And if we fold this in the form of a ring, this point and this point will overlap. So this is a finite chain with 10 unit cells or one atom per unit cell. So therefore, each red point represents a K values, allowed K values in the first Brillouin zone. In between the two K values, there is no allowed K values. For long but finite chains, if we increase the number of atoms in the ring, the points are very dense. If we have very large n, so every lattice point will have neighbors, will have close neighbors. So it will look like a continuous curve, but actually there will be only n. There will be allowed K values that would be equal to the number of atoms in the crystal. Is it clear to you? If it is clear, then we proceed further. If you have any question, you can ask. So next, after discussing if we have understood the vibrations of one-dimensional monoatomic chain, then we can expand this knowledge to the case of 2 atoms per unit cell. So such examples are, for example, sodium chloride, potassium chloride, or cesium chloride, or diamond, in which we have the basis of 2 atoms. The basis of 2 atoms, or the unit cell, contains 2 atoms. So in order to understand the lattice vibrations of one-dimensional diatomic chain, we take the example of, for example, sodium chloride, in which sodium is a smaller ion and chloride is the bigger ion. And this is what represents the sodium chloride in one dimensional. This is a one-dimensional chain consisting of diatomic molecule of sodium chloride. The black smaller circle represent here sodium ion, and the open bigger circle represent here the chloride ion. So we can represent every ion. So for example, this is the nth ion of sodium, which is surrounded by two chloride ions, or if we have nth chloride ion, it is surrounded by two sodium ions. Now, in this case, we define the interplanar space, interatomic distance is the distance between two chloride ions or two sodium ions by, it is 2 times. So we represent it by B, and it is equal to 2 twice of A. So in this case, the interatomic distance between the similar ions is equal to 2A. And if it is represented by B, so the reciprocal lattice vector corresponding to this B would be equal to 2 pi over B. Because these are different atoms, one is sodium atom or ion, other one is chloride ion, when they vibrate, their amplitude of vibration would be different. But for every sodium ion, the vibration would be the amplitude of vibration and frequency would be the same, and the amplitude and vibration for all chloride ions would be the same, but it would be different for chloride and sodium ion. So if we consider the motion of two different ions, their vibrations would be given by these equations, which we proved yesterday. This is M is bigger ion, chloride ion, M delta second derivative of its displacement xn is equal to k bar, which is a spring constant, and delta yn plus delta yn minus 1 minus 2 delta xn, and M delta second derivative of yn would be equal to k bar delta xn plus delta xn plus 1 minus 2 delta yn. Now you can see here we have a mixing. Here we have xn, yn. I think you can understand it, because if we consider the vibration of this sodium ion, it is given by yn, but its vibration is coupled with the vibration of chloride ion. That's why we have xn and xn plus 1 here. Similarly, if we see the motion of this nth ion of chloride, which is given as yn, it is surrounded by two sodium ions. That's why we will have yn and yn minus 1 here. Is it clear to you? Is it okay with you, the two equations?
Yes, sir.
So their solutions will be in the form of a traveling wave given by these equations, and if we substitute these equations, in the above equations, we are, after solving a little bit mathematics, you can do it. We will have these two equations: minus capital M omega square times A is equal to k bar B times 1 plus e to the power iota kb minus 2 k bar A, and the second equation would be minus small m omega square B is equal to k bar A times 1 plus e to the power minus iota kb minus 2 k bar B. We have two equations in the coefficient in A and B, and these equations would be satisfied if the determinant formed by the coefficients of A and B is equal to 0, which is known as the secular determinant. In this course, we have done this exercise several times. So if we write the coefficients of A and B from the two equations, and we in the determinant form, and we write the value of determinant equal to 0, we can solve this equation. And after a little bit mathematics, we are going to get this equation. Omega square is equal to k bar inside the bracket 1 upon capital M plus 1 upon small m plus minus k bar under root 1 upon capital M plus 1 upon small m to the whole square minus 4 capital M times small m times sine square kb by 2. And this is the equation that is having plus minus. So it will have two roots. So one root will belong to plus value and the other root belong to minus value. And these two roots are given here. And these roots are given name as optical branch and the acoustic branch. Please see the pronunciation. It is many people write its spelling incorrect. ACCOUSTIC they write. The correct spelling is ACOUSTIC and the pronunciation is acoustic. Acoustic, not acoustic. Acoustic is the correct pronunciation. So we have the relation, the dispersion relation between frequency and wave vector for the acoustic branch given by this equation, and for the optical branch the relation is given by this equation. And the name why we are calling one branch as optical branch and the other one branch as acoustic branch would be clear to you in a short while. Now if we plot it, then we will see that for each k value we find two normal modes because we have two branches. So each k value will correspond to two normal modes, and since there are n different k values in the first Brillouin zone, therefore we obtain 2n normal modes, 2n ways of vibrations in the first Brillouin zone, and this is what is shown. You can see, you can take any arbitrary value of k in the first Brillouin zone and you see it will have one solution in the acoustic branch and the other solution in the optical branch. That's why we say for each k value we find two normal modes, and because there are n different k values in the first Brillouin zone, therefore we will have 2n normal modes or 2n different ways of vibrations in the first Brillouin zone. You see, the acoustic branch is the same as that of a one-dimensional monoatomic chain dispersion relation. It is the same, but along with this, we also have this branch of higher frequency. On the y-axis, you see the frequency increases like this. So on the higher frequency side, we have the branch that is known as the optical branch, and in between the optical branch and the acoustic branch we have a forbidden gap. This curve is more or less similar to what we discussed in the nearly free electron model, isn't it? In the nearly free electron model we also have a forbidden gap, not allowed values, and here also we are having not allowed values. So the optical branch and the acoustic branch are separated by a gap that is known as the forbidden gap, not allowed values of k. So the waves in the forbidden region are directly attenuated by the crystal, which behaves as a mechanical pass filter. So if we have any elastic wave whose wave vector is such that it will give the frequency which lies in the forbidden gap, then crystal will not allow this elastic wave to pass through it. That's why it is a forbidden gap. So now we understand acoustic branch at near k is equal to 0 at the center of this zone boundary, the lower branch, which is acoustic branch, it represents long wavelength elastic waves with a frequency independent velocity. Here you see it is more or less linear, so omega is Vs times k, and the longitudinal elastic waves are identical with the sound waves. However, in the case of optical branch at k is equal to 0, you see the curve is like this for optical branch at k is equal to 0. The frequency of this optical branch lies in the infrared region of the spectrum. So incident light will be scattered if the incident light is in the infrared region, and if such light is incident on, for example, sodium chloride. We have a sodium chloride crystal, and we have the incident light wave that whose frequency lies in the infrared region. So such waves would be scattered from the sodium chloride crystals. That's why this is the reason why the ionic crystals respond to the infrared spectrum of electromagnetic radiation. The optical mode also has zero group velocity at k is equal to 0. Here you see the curve is flat, therefore the group velocity for this optical branch at k is equal to 0 is 0. The curve here is flat. So for acoustic branch near k is equal to 0 long wavelength limit, we have the equation for acoustic branch. If k tends to 0, sin kb by 2 will tend to kb by 2. And under this limit that k tends to 0, after doing a little bit mathematics, we will get omega minus is equal to ka divided by under root 2k bar divided by capital M plus M. And for this, phase velocity is equal to omega minus divided by k. It will come out to be b under root k bar divided by capital M plus M, and we denote it by v. Group velocity will be d omega by dk. That would be also equal to same. So again, in the acoustic branch under the long wavelength limit, the group velocity and the phase velocity are same, as we have seen in the case of one-dimensional monoatomic chain. As k increases or wavelength decreases, acoustic branch initially increases linearly, then it slowly decreases and eventually saturates at the zone boundary, that is plus minus pi over b or plus minus pi over 2a. What is the maximum frequency? What is the maximum frequency for this acoustic branch? It comes out to be under root 2k bar divided by m, and this is what is shown on the curve. It is under root 2k bar divided by m. This is the maximum frequency that belongs to the acoustic branch. And you see we have the capital M in the denominator. That's why this maximum frequency of the acoustic branch is independent of the lighter atoms, or independent of the, in this case, independent of the sodium atoms. It only depends upon the mass of chloride ions. Now we would like to see what happens for the optical branch. At the zone boundary, we will have the minimum. You see, the frequency here is decreasing and it is minimum at the zone boundary. So it will be under root 2k bar divided by small m. It is the minimum frequency of the optical branch. And it is independent of the heavier mass. It is independent of the heavier mass. It only depends upon the lighter ions mass. Near the center of the Brillouin zone for this optical branch, the maximum frequency would be 2k bar under root 2k bar times 1 upon capital M plus 1 upon M. This is the maximum frequency for the optical branch. The width of the forbidden gap depends upon the ratio of the two ions, heavier ion to the smaller ion. The larger is the ratio, the greater is the width of the forbidden gap. If we have the two masses equal to each other, that is capital M equal to small m, forbidden gap disappears and optical and acoustic branch coincide at the zone boundary. And this is what we expect. This is what we expect. So first Brillouin zone for this one-dimensional diatomic frame is either from minus pi by b to plus pi by b to pi by b, or it is from minus pi over 2a to plus pi over 2a, and the smallest wavelength corresponding to first Brillouin zone is of this wave vector a equal to pi over 2a. So the shortest wavelength that can belong to the this crystal is of 4a wavelength. We can now investigate the physical difference between the vibrations represented by the optical and acoustic branches. So for optical branch, when k tends to 0, e to the power I iota kb will be equal to 1, and e to the power minus iota kb will also be equal to 1. And we will have the equation where we will have the relation between the amplitudes, the masses of the two ions. A upon b would be equal to minus small m divided by capital M, which indicates that two atoms move in the opposite directions because we have a minus sign here. A is our bigger ion, and its vibration is inversely proportional to its mass. B is the lighter ion, its amplitude is inversely proportional to its mass, and we have minus sign here. So this means that the two atoms move in the opposite directions and their amplitudes are inversely proportional to their masses, so that the center of mass of the unit cell remains unchanged. So when we have lambda is much greater than b, you can see here b is the interatomic distance between similar kind of ions. So here we saw a wave for which lambda is much greater than b, and the ions are moving in the opposite direction. The open circles are moving, for example, here it is moving up, but the lighter atoms shown by the filled circle, small circles, they are moving in the opposite direction. When the open circle or the heavier ion is moving in the in downward direction, the lighter atoms are moving in the upward direction. So their motion is in the opposite direction. This is the mathematical representation of this equation for the optical mode. If we have the two masses equal, then this ratio A upon B would be equal to -1. The atoms always move in the opposite direction. This is clear. So for what will happen for the acoustic branch? When k tends to 0, omega tends to 0, and the ratio of amplitudes of vibration of two different ions A over B would be equal to +1. This means the two atoms move in phase and their center of mass also moves. So this can be represented by this way. K tends to 0 means wavelength is very large. It is much larger than the interatomic distance. So on this wave you can see atoms, the different atoms are moving in phase with respect to each other. This is for acoustic branch, but for optical branch, the two atoms vibrate opposite to each other and their amplitudes are inversely proportional to their mass. So with this, I think I should stop here, and Remaining remaining lecture we continue in the next class.